Okay, so now I'm going to explain to you Taylor's theorem, at least the first part of Taylor's theorem, and how we can use it to understand the linear approximation to a function. So just remember, let's think about Taylor's theorem for a function of one variable. So it said the following. Say you have a point x naught here and a point x. Let's say that you know the value of f at x naught, and you want to estimate this point, so you don't know what the value is. So what Taylor's theorem says is that to some reasonable approximation, which can be made quantitative, f of x can be approximated by the value of the function at that point, f of x naught, plus the derivative of the function at that point, f prime evaluated at x naught, times x minus x naught. Okay? And so if you write it that way, this tells you that one way to think about this, and let's see how I want to say this. Well, yeah. Right. Think about the equation of a line. So there are many ways to write the equation of a line. One way was like y equals mx plus b. But if you have 2 points on the line, one other useful way to write it is y minus y naught equals m times x minus x naught, right? Or in other words, y equals y naught plus m times x minus x naught, right? And so if you compare the approximation, the first order approximation with this term corresponds to this term, right? Y naught seems to correspond to this term, and f prime seems to correspond to the derivative. In other words, what I'm trying to say is that just from the first order Taylor approximation, you would infer that the equation for the tangent line should be, so the equation for the tangent line meaning this equation should be y equals f of x naught plus f prime of x naught times x minus x naught. Okay, and again, this is a line whose slope is the first derivative, and at the point x naught, it passes through passes through here, so it's actually tangent to the curve, and it's basically the one that you are after. So now we can do some smart speculation to infer what the equation of the tangent plane should be for a function of two variables. I'll later give an explanation which is a bit more general and more geometric, but now this is just like a good heuristic to keep in mind. So if you have the graph of this function, now you have a point x x naught, y naught. Now you have another point x comma y. You have this point which you do know. You don't know this value. You want to estimate it. Okay? So the linear approximation in this case, as you might expect, would tell you that f of x comma y is approximated by f at the point for which you know the value, and now here comes the cool part. So we need to find like a useful replacement for this expression. So this expression involves a derivative. Now, well, which derivative should you put? Essentially, you should put both, right? There's no the two candidates for derivatives are the partial derivatives in this case. So you could take, for example, the partial derivative of f with respect to x and evaluate it at x naught, y naught. Okay? So this is playing the role of this term. And then the question is, what should you multiply it by? Well, you should multiply by x minus x naught, because first of all, it has to be something linear, and you're making a rate of change in x, and so this is like a delta f over delta x, and this is like delta x. So the delta x cancel, and that's why you get like a small change in f, which is what you're trying to measure. If you put here y minus y naught, you get like delta f over delta x times delta y, which does not have like a useful interpretation in that sense. And then you can put here times y minus y naught. Okay, so that means that the equation for the tangent plane, and that's the next video I'll do an example about a linear approximation. But the equation for the tangent plane at this point is the value of the point plus the partial derivative of f with respect to x at that point times x minus x. It's just essentially what I'm writing here. So in case you cannot see everything that is, sorry, small size. Okay. So in the next video, I'll do an example about this linear approximation so that you can see how this is supposed to work. And already in this linear approximation, you can see something else that's being hidden, which will be called the gradient. But I'll tell you more about that later. So this is an illustration of Taylor's approximation. In this example, the function is sine of x times cosine of y plus 2. And so, for example, the first approximation in Taylor's expansion is the linear approximation. So for this particular function, it happens to be this expression. The specific constants do not matter that much. The important feature here is that this is precisely the expansion that gives, from which you can extract the equation for the tangent plane, which is why you see a tangent plane here. And if you keep moving the point, you see the linear approximation changes as you move along it. Now, it's also useful to know, especially when you start studying the classification for critical points, that you can keep going in the Taylor expansion. So for example, you can do the quadratic Taylor approximation,
which okay, this one is again a bit more complicated to show you. Let's see. Oh, it looks like this expression, and now the graph, if you take a look at it, is a lot more it resembles a lot more the actual, the approximation resembles a lot more the graph of the function. Okay, and you can keep going. Like for example, you can do the degree 3 Taylor approximation, which looks a lot better. It's harder to distinguish it from the actual graph of the function. And for example, here's the, okay, now you cannot even see the degree 3. It's a bit of a mess, but if you go to the application, you actually see a formula for it. It's just that it got confused here, so you just have to trust me on that one.